Hello and welcome to today's webinar, Geological Considerations and Parameters for Soil Permeation Grouting. My name is Jessica Williams and I am the Marketing Manager at Avanti and will be playing host and moderator for today's event. But before we get started, I want to remind all of you to use the question function in the GoToWebinar panel. We'll have about a 10-minute Q&A section at the end with both of our speakers. So if you think of anything that you may want answered, go ahead and add that into the question box and send it our way. Now I'll let our speakers introduce themselves and then we will get started. Brad?
Thanks, Jessica. I'm Brad Crenshaw. I'm the General Manager for GEC Drilling and Grouting. We're a contracting company out of Tennessee. We perform contract grouting work on primarily heavy civil and mining jobs, primarily throughout the U.S.
All right. Thank you, Brad. And my name is Britt Babcock. I'm the president for Avanti International. I've been in and around construction and engineering for the last 25 plus years and been with Avanti for 10 and really taken a hold and loved getting into the grouting industry and looking forward to having a great presentation today with everybody.
Great. Thank you, Britt. And before we get into the meat of this presentation, we're going to have a couple of poll questions just to keep it engaged. So the first one's launching now. And it is, how often do you use grouting in your job? Always, usually, sometimes, never. Give you a few seconds and we'll share the results. Got about 50% of the responses in. Give it about 5 more seconds. All right. As you can see, 65% say sometimes. So it's a pretty high number.
That's great.
Yeah.
Yeah.
All right. Now I will let Britt.
All right. Thank you, Jessica. Before we get started, one of the best things to do is define, since we're talking about grouting into soils, permeation grouting into soils, is to really define what is an injection grout. Well, injection grout is a liquid resin that turns into an impermeable solid in a predictable time frame. And that could be not only just a resin, but also a cementitious type material that does turn into that solid. This happens to be a picture of a chemical grout, one of our acrylics, A and B, and turns into a gelatinous material that can easily permeate into the soils. But it's best to know what we're talking about. Where are they used, or what's the goal for the injection grouting? Well, there's no matter what type of project or application you're on, almost inevitably it can be boiled down to the goal of stabilizing the soil or the rock in and around that structure, or filling voids, or controlling groundwater. So where are grouts used? Well, it's a myriad of different locations. One is mainline sewers, laterals, and manholes to control infiltration of the groundwater through the cracks or through penetrations within that system. There's also soil stabilization. In this particular photo, you'll see that there's been ultrafine cements impregnated into these sands, or permeation grouted into these sands, in order to stabilize the sand and to maintain structural integrity of the building above. If that wasn't there, obviously sands would funnel out and cause that building to settle. Also, hazardous waste containment is another application, whether it's hazardous waste or an environmentally sensitive material that needs to be encapsulated and captured. So another location is subways and tunnels, whether it's during construction or post-construction, either in cracks within the structure itself, or curtain grouting on the outside, which is what's depicted here, as well as the egress spaces, the train stations and different things that are subterranean. So where else do they get? Mines, tunnels, slopes, and shafts, a myriad of applications there. Concrete and earthen dams, whether it's in the tunnels within the concrete dam or within the face itself, or in and around inside permeation grouting inside earthen dams as well. Beneath structures for either stabilizing the soils beneath those structures, or water control for tunnel egress within those buildings. break in and break out for TBMs, tunnel boring machines. Grouting can become a useful tool in those situations on occasion. Tunneling the TBMs. TBMs sometimes need soil stabilization either way out in front of it or during construction. This happens to be one where they were in a homogeneous clay and hit a sand pocket, and so that sand had to be stabilized before they can continue on. Pre-excavation dewatering as well. This is a combined sewer overflow outfall tank. A lot of artesian water pressures here, so they had to grout in and around that in order to allow for constructability. But today's focus is on soil permeation grouting. And before we get started, now that we know where they've been used, we've defined it. What are the typical types of grouts? Well, there's two types. There's cementitious grouts. Within the cementitious grout family, you've got an ordinary Portland cement, either type 1, type 2, or a type 3, or you'd have an ultrafine. Now, of course, I'm combining microfine, superfine, and ultrafine all into that one category, but we'll define that a little bit deeper here in a few minutes. And there's also solution grouts. Solution grouts combine of your polyurethane grouts or polyurethane foams, which most people recognize them as. And within that, the subcategories are hydrophilic or hydrophobic foams. And you've also got your chemically reactive grouts, your acrylamide, your acrylates, your acrylics, and your sodium silicates. Jumping into cement and cementitious grouts, obviously I just talked about the Portland cements. We have type 1, type 2, average micron sizes anywhere from 50 to 100 microns, whereas then you get into the type 3 Portland cements, and those are 15 to 20 microns. And then even further refining those micron sizes, dropping down to the single digits, we get into the microfine cements, which have an average of 8 microns, and the ultrafine cements of 3, and superfines of 1.5. To put that in perspective, your human hair is about the size of 70 microns, to give you an idea of scale, relative scale there. This shows just how fine those cracks and fissures can be impregnated with ultrafine cements. You can see that they get very, very fine. And there's some standard rules of thumb for that. Hopefully you saw our rock webinar presentation last time. If not, you can definitely jump back and get educated on rock grouting. We had a whole series on that, or whole webinar. So what comprises of an ultrafine cement? Well, it's actually just Portland cement and some type of pozzolan. Type of pozzolans that are typically used is a slag. Man-made pozzolan is slag. That's a predominant man-made pozzolan. There are coal ash, silica fume, and VCAS, but slag is really the predominant one that's the man-made pozzolan. And it's a byproduct of steel manufacturing process. There's also natural pozzolans, and it's the predominant one used within the natural world is pumice. There are metakaolin, calcine clays, and diatomaceous earth that could be used as well, but predominantly it's pumice. And also we have viscosity modifiers that get used within the cementitious grouts. There's naphthalene-based superplasticizers, also known as water reducers. When you hear that term, that's what that means. It is a superplasticizer or a water reducer. So naphthalene is one type. Polycarboxylate is another typically type that's used. And then also to control bleed, gums that get used are whaling gum or diatom gum. So now jumping into the chemical grouts, talking about the solution grouts. Solution grouts is a general industry term there. Polyurethane grouts, again, two families, hydrophilic, hydrophobic. We've got a strong affinity for water within the hydrophilic family, like fill with water. That's kind of how I separate that analogy. They're typically single component. They react with the water. When they become in contact with water, that begins a reaction. They tend to have moderate expansion, and they're difficult to accelerate. Sometimes you can do that through heat. They are temperature sensitive, just like any chemical grout. Whereas you get into hydrophobics, they have little or no affinity for water. Some of the hydrophobics require just a little bit of water to react. Some of them don't require any. They're a dual component. You can have a part A, part B that reacts it. Hydrophilics tend to have a catalyst. In the industry, you'll hear that term as an accelerator as well. And you can change the set time on that. And they tend to be highly expansive. They can be anywhere from 20 to 30% expansion. So viscosities for the polyurethane grouts are low. They go from anywhere as low as 35 to 50 centipoise up to 3,000. Water being 1 centipoise. So to give you a frame of reference there, 35 to 50 is like vegetable oil. Or 3,000 centipoise is like maple syrup. So reaction times for the urethane foams can be anywhere from a few seconds upwards to 30 to 45 seconds to a minute, or 2 minutes or more, depending on how cool it is or how cool the material is. But bouncing into the chemically reactive grouts now, those are comprised again of the acrylamide, acrylics, and silicates. They're always a two-component system, a part A and a part B. Viscosities are relatively close to each other. The acrylamides and the acrylics are ultra low, typically 1 to 2 centipoise. The acrylates and the silicates, acrylates tend to be 3 to 4, where the silicates can be upwards 8 to 10. That doesn't sound like a large variance, but believe it or not, that can make a difference on your permeability into a soil. They basically permeate anywhere water can travel. There are controllable set times. Acrylamides generally, and acrylics and acrylates upwards to 10 hours. I've seen it push beyond that envelope, upwards to 15. And then sodium silicates, roughly about an hour. So just a quick snapshot. Again, part A, part B, mix those together and you get a gelatinous material. Now this is a neat sample. Obviously this would be injected into a soil to create a permeation grouting application. So chemically reactive grouts, the acrylamides, they're organic based. To kind of tell you about those, they were invented in the mid-20th century, predominantly used for water control, not for structural, low viscosity, long design life, manageable toxic components, and they're inert, non-toxic, and irreversible when cured. Jumping into the acrylates, they're organic in nature as well. They were invented in the 80s. They're basically a pre-polymerized chain of the acrylamides, and then it jumps into, which creates an acrylic type grout. Water control only, again, non-structural, slightly higher viscosity, shorter to medium design life. Controllable set times, even though it says an hour, I've seen it taken out to 10. So, and then a non-toxic component as well. Sodium silicates, they're inorganic. Oftentimes the slang term for sodium silicates is water glass. They have a very, very small particulate within it, down to like 0.3 microns, I believe, or something like that. Very small. Even though technically it's a particulate, it's so small that it acts just like a solution grout. So first used in the late 1800s, believe it or not. They are considered temporary in nature, depending on who you ask. There's varying opinions out there, but general standard industry consensus is temporary. Excavation support and underpinning are the applications. They have good, reliable compressive strengths. They can be susceptible to syneresis, and the control times are generally less than an hour. All right, Jessica, I'll pass it on to you.
Okay, great. Thanks, Britt. So now we'll launch poll question number 2. Should be on your screen now. And the question is, if you're involved in permeation grouting, which type of grout do you use most? Microfine, ultrafine, chemically activated, polyurethane, silica, or none of the above? All right, votes are coming in. We'll give it about 10 or so more seconds. All right, we'll close it, share results, and it's pretty much almost an even spread. 30% say none. Yeah.
Oh. We have 30% we need to convert. All right.
All right. Britt, back to you.
Thank you, Jessica. All right, now that we've defined what a grout is, we've defined where they're used, basically anywhere water needs to be controlled or ground or soils need to be stabilized. And we defined what they are as an overall view. Which grouts are used, when, and why is really the great question, right? We get that all the time as in our industry as suppliers and manufacturers of the grouts. There's really 2 types of grouting: penetration grouting versus permeation grouting. Penetration grouting, also known as rock, and then soil grouting or permeation grouting into sands and gravels is the other type of grouting. There's matrix porosity, which technically is a phenomena of geology or bedrock geology. However, we put it under the permeation grouting because you grout it just like a soil, same practices, same techniques. But today we're going to talk about soil permeation grouting, and the grout types used in soils is basically all of them, right? You'll see I've got listed everything here. Well, that's got to be clear as mud. You know, it's got to be frustrating to say, okay, I need a permeation grouting job. What grout do I use? Well, I don't know. It depends. Well, let's add some clarity into that mud, if you will. There's three factors that affect grouting when it comes to soil permeation grouting. Three primary factors. The first one is grain size, fines content, and permeability. Why does grain size matter? Well, first let's define grain size so we have a better idea of that. Obviously, there's two predominant soil types in the world: granular and cohesive, sands and or clays, if you want to really boil it down to general terms. But granular is gravel, stone, and sand. They tend to not change with water. They're little particulates of stones or sand and gravel, obviously getting bigger in size, upwards of 3 inches or more. Whereas in the cohesive world, you've got clays and silts. They tend to have a plastic consistency and they change with water. So in the grain size of a granular material, that can range from 3 inches down to just barely visible by the naked eye. Well, think about if this were an angular material, 3/4 inch or 1 inch angular material with fairly good porosity, we're going to be able to pump almost anything into that from a permeation grouting perspective, including the kitchen sink, right? Whereas even though it may be a relatively clean material, maybe we're looking at a sugar sand, those grain sizes are going to be so fine that it's not going to necessarily just take anything. It may only take an acrylic type grout, an acrylamide or acrylic. So grain size matters. The next thing it also matters, the second factor is fines content. You'll hear this referenced as fines content, how dirty is the material, what's the -200. Those are all one and the same measurement of the soil. Well, what we're measuring is the silt and clay particles within soils. So anybody familiar with the USCS, Unified Soils Classification System, will recognize that these all follow what it recognizes as clean material, slightly silty or silty clay. We found that aligns really well. So anything from 0 to 5% considered a clean material, you're going to typically, as long as the grain size will allow, you're going to be able to just pump an ordinary Portland cement. You could do an ultrafine, a polyurethane, or a chemically reactive, but because of the cost, you're probably going to go to an ordinary Portland cement as your first choice. Now, as the material gets dirtier to a slightly silty, slightly clay, between 5 and 12%, an ordinary Portland cement is going to fall off, and you're going to bounce into and require the need of an ultrafine cement. Could you use a poly and a chemically reactive? Sure, but it may be that you could use an ultrafine cement, and ultrafines will get more difficult as this gets dirtier. But then you get into silty clay material, 12 to 20%. You're probably into the chemically reactive material. So Brad will talk more about that here in a little bit. But how do we determine the silt clay content of a material? Well, it goes through a gradation analysis, and there'll be a sieve called the -200. And the reason it's called the -200 is there's 200 small openings within an inch there. So it'll pass through whatever particles the naked eye can't see. The next factor is permeability. Q equals KIA. Q is flow, K is the permeability value, I is a factor, and A is the area. So when you're looking at the permeability of the K values at a range of 10 to the -1 to 10 to the -4 centimeters per second, okay, that's going to be fairly permeable. So now we're looking at the same thing. Probably an ordinary Portland cement will be your first choice. As that material starts to tighten, gets less permeable from a range of 3 to 5, now you're probably looking at an ultrafine cement, a poly, or a solution grout. And then as it gets even less permeable, that range tightening to 4 to 7, now you're probably looking at a solution grout like chemically reactive grouts. So one of the questions we get a lot is, what's the difference between permeability, porosity, and void ratio? Sometimes those terms are used interchangeably, but they are not the same thing. So we thought that we would add some definition to that. So permeability, what is that? It's really the measure at which a fluid can move through a soil or a rock. So now when we talk about porosity, though, porosity is actually the open space. That's actually the void space within that mass material, whether it's a rock or a soil, between the grains of sand, grains of rock, grains of particles. So, and then void ratio, you'll hear that thrown around quite a bit as well. Even though the intent is the same, everyone in the conversation may understand what you're saying. That's really the ratio of the voids to the volume of the solids. So just recognize that those are different terms, but when you hear them, realize they're really probably talking about porosity is what they intend to say. Just a quick snapshot of some different porosity values for different materials. I just thought this would be fun to throw up there. Sands can be anywhere from 25 upwards to 50%. Whereas if you get into gravel, it can get even more or less. It's going to vary based on the type of material you're in. So life expectancy of grouts, we get that quite a bit. Oftentimes it's a key decision factor when deciding to grout and which grout to use. AB100 acrylamide was tested by the US DOE, even though it says 362 years. When you factor that back, we can get over a 50-year design life, and you can get up to over 100 years when you consider the grout concentrations, things like that. Cements, up to 100 to 200 years, depending on who you ask and what's in the ground that may attack it. Polyurethane, 75 to 100 years. Acrylates were tested during that same DOE study of 54 years, and then sodium silicates, anywhere from 2 to 10 years, depending on who you ask. Obviously, opinions vary in the industry. Question we get often is average grout material cost. And believe it or not, a lot of times grouts do not compete with each other. It's Mother Nature that dictates what grout is going to be used most of the time. For this quick scale of reference, Portland cement being the least expensive here at the bottom, whether it's a type 1, type 2, or even a type 3. Then you'll get into sodium silicates, and the price just starts to increase per injected gallon. Ultrafine cements, acrylamides, acrylates. And then most expensive will be your polyurethanes, which is most often why you don't see them used on a large scale grouting operations, just from a sheer cost. Also has to do with usability and functionality for the application as well, but definitely the most expensive in the scheme of that scale of grouts. All right, Ms. Jessica.
Great, thanks, Britt. So this is our last poll question, and it is launching now. Should be on your screen. And do your grouting projects typically require grouting of rock or grouting of soil? Both? Neither? We're collecting responses. We'll give it about 10 more seconds. All right, we'll close it, share it. All right, 44% say both, and the next 34% say soil. All right, great. So now we'll have Brad take over.
All right, thanks, Jessica. Thanks, Britt. So to follow up, then Britt has already gone into a pretty good amount of detail about what different types of grouts you can use and the considerations of why you would use those and the soil types. I'm going to touch on that just a little bit because there's just a couple other factors that I want to hit. But other than that, I'm mainly going to go into how the geologic factors on a project kind of affect the design and the implementation of a soil grouting program. But just follow up on what Britt said, I mainly wanted to provide this chart here for reference in case you want to go back to later to reference this presentation. And I like this chart myself, even though it is a little bit older. It's from a 1995 reference, as you can see down here. But essentially what it does is it provides you a general idea of the types of grouts that can be used in various types of materials. And what I like about it is it kind of gives you an idea of the results you may be able to expect. So you can see the grout types that are listed over here on the left-hand side. And actually, some of these really probably aren't used anymore, but still a lot of them are. So I think it's a good reference. But the way that you read this is that if you go and look at the grout type, so here we've chosen, these are Portland cements. This is the range of hydraulic conductivities that they can typically be injected into. So here you can see a range of about, it looks like 10 to the negative 3 down to about 10 to the negative, 10 to the negative 2 up to about 1. And then it can be injected into that, which typically corresponds with gravels, as you can see at the top. And the result that you should be able to expect is somewhere in this black arrow here, and it may extend down to the dashed arrow. So you should be able to expect a reduction in hydraulic conductivity of about, somewhere between 2 and 4 orders of magnitude, as you can see. So, again, I think it's reasonable. I think it gives a good idea of if you have a certain soil type where you may be wanting to look for the type of grout. But I do want to point out go on to what Britt said. So I have a note down here, and the fines content of the soil is very important. As you can see, the sort of rule of thumb that I typically use is that soils must be less than 50% fines to be groutable. That's going to vary. It's going to vary, I think, probably depending on the exact grain size and soil type and things of that nature. But typically, you're going to see 12 to 22% probably is the range. Once you get beyond 22% fines, then that soil is typically not going to be able to be permeation grouted. And the reason is simply because those fine materials just fill up too much of the void space for a pathway to be created that you can permeation grout through that soil and get a repeatable, consistent penetration into the soil. I did want to point this out here. This is actually rock, and this is a slide from the last presentation. Britt kind of mentioned this during his slides. Granted, this presentation is about soil grouting. However, there are rare circumstances where rock needs to be grouted like a soil. It needs to be permeation grouted. And I wanted to point that out here, just reiterate what we said during the last presentation. And what this is showing, this is a poorly cemented sandstone on the right. So this is the rock face of a shaft. And on the left, this is a 3D printout of a rock core that in a sandstone that shows 60% void space of that rock core. So this is a rock in which 60% of the space is actually not filled by any material. And that is similar to the rock that's shown on the right. So you do get into those situations, and again, that's rock grouting, but in situations like that, you would grout those similar to the methods that you used for permeation grouting of soils. So just want to bring that up. Now, getting into sort of the practical aspects of the application of soil permeation grouting and into the geology and how that affects your grouting program and how you're going to go in and design that program and implement that program, then probably one of the key factors that most people want to understand after which grout do I use is how much grout do I need to use? And theoretically, it's a relatively easy principle, theoretically, because we essentially consider making cylinders around a grout hole. And as you can see here from this diagram, obviously the equation for the volume of the cylinder is pi times r squared times h. So you can, that's shown here. You got a height, you've got a radius. But whenever you're doing that for grouting, there's another factor that you kind of have to consider in there, and that is in that theoretical cylinder, how much of that space can be filled by grout, because some of that space is going to be filled by the soil material itself. So as you can see, I've added over here a grout hole, which is called as a sleeve port, and I will go into a little bit more detail about what a sleeve port is and how that works later in the presentation. But essentially consider that the grout hole. That's the way to look at it. You can go down. That grout hole is going to have a point where you inject the grout from, and whenever you inject the grout, because you are considering this soil as somewhat of a homogeneous material, then the reason that we're considering this cylinder is because we expect a somewhat similar spread away from the grout hole. And so, again, to take into account how we figure this, you're going to have a height of, that's going to be a stage, an injection stage. You're going to have a radius that's going to be a spread away from the grout hole, which is going to play into grout spacing. But then we also have to figure out how much material gets placed into that cylinder. So the first thing, how do I go back, Jessica? Okay, perfect, thanks. So the first thing that you have to determine is the radius. And one of to figure the volume, you have to do that. But also that's important because the radius is going to play into what your hole spacing is going to be. You need your grout holes, you need these theoretical cylinders to touch and somewhat overlap, just so you have a little bit of a conservancy in your design. So to do that, you need to know the radius. To figure what that radius is, then you need to consider the hydroconductivity or the permeability of the soil. You need to take into account the viscosity of the grout. Britt mentioned that these grouts have various viscosities, and really what viscosity is telling you in the soil is essentially how fast you can pump grout through the soil. So you can pump a less viscous grout into the soil faster than you can a more viscous grout. And also, you need to take into account other properties of the grout, such as the set time. It was mentioned earlier that some chemically reactive grouts, solution grouts, have set times of about an hour, where some have up to 10 hours. So obviously, if you can pump grout longer, you can push it a further distance, i.e. radius, away from the injection point. Then you have to figure in the height. So the height or a stage length, really, a lot of the times that's, if you are in it's going to be standard. Oftentimes that's going to be 16, 18, 24 inches. The key thing to look at here is differences in your geology. If you have major differences in geology, you need to consider that. The example that I show here is just a boring log that I pulled from somewhere, and the lower, so there's a grout hole, which is indicated by this blue line here, and the stage, the grout zone, is between two packers, which are indicated by the red spots in this grout hole. So this is the zone in between those two red spots are what we're grouting. And as you can see, the lower portion of that zone is a gravel, and the upper portion is the sand. And just theoretically, I didn't have the data on this, but just to prove the point, to show the point, then the assumption is that the gravel has a much higher hydraulic conductivity or permeability than the sand does. And so the orange over here indicates a potential spread of the grout. And what you can see is that because you have this transition in geology, then you actually get a much further spread of the grout in the gravel than you do the sand. And you really don't want that. The idea of this theoretical cylinder that you have is really to have a controlled spread of grout. If you don't know where your grout is, you really don't know the results that you're getting. So in this case, then you may want to do a stage in the gravel zone in which you pump less grout, or which you pump grout for a shorter amount of time or at a faster rate, and then a zone in the sand which you pump at a slower rate, but to get the same spread as in the gravel due to the difference in permeability. Now, the next factor that you have to figure out is the space that you need to fill up in that soil. So this is i.e. what is inside the theoretical cylinder. And a lot of times what people want to do is they want to use porosity. And that's not 100% wrong, but it's also not 100% right. So essentially porosity is the percentage of void space in a geologic medium. The equation's there. To demonstrate why it may not be right all the time. Now, obviously, this is rock, shown here on the left, is pumice. But to demonstrate this, all of these little black spots indicate air bubbles, essentially, in this pumice. So that's void space that's in this material. And this void space is really not connected. Even though this is rock and it's easier to see here, that premise can also work in soils. So that presents a problem if you're looking at porosity. So porosity, again, percent void space. Permeability is essentially how well connected is that void space and how easy is it to push a fluid through it. So when you look at this pumice here, then the porosity, so the void space, is typically 64 to 85% for a specimen of pumice. However, the permeability is very low, less than 10 to the -7, which essentially means you can't push much through that. So even though you have a very high porosity, the amount of material that you could push in that space would be very low. Britt went ahead and he had a better chart than I did on this, but again, I wanted to make this example. You can see on the top here, you've got sands and gravels, typical porosity ranges from 25 to 50%. Sand and gravel mixed is lower simply because you have different grain sizes, so they fill in those spaces. Glacial till, lower along the same principle. But then you get into silts and clays, and actually silts and clays have really high amounts of porosity. However, the permeability, hydraulic conductivity, is very low. It's hard. The grain sizes are so small that you can't really, it's hard to push a fluid into those. So these, even though they have very high porosities, are not really considered, these silts and clays are really not considered groutable per se. And not all the space in these sands and gravels and till would be groutable either. But then that still brings up to the point of how do you determine what that groutable void space is going to be? Well, it's going to be based off of the soil characteristics, which, as we said, porosity plays into this, but also the permeability plays into this, because how much of that space can I actually get something into is going to be based off of the grout properties, because a less viscous grout can be pushed in longer and faster. Also, a solution grout can be pushed into more spaces than such as a acrylic or sodium silicate can be pushed into more spaces than a particulate grout, such as an ultrafine. But finally, part of figuring that out is just going to be based off of experience and having dealt with different types of soil conditions before and a reasonable, educated assumption. Can you go back one more, Jessica? Go back again. So as you're doing the work, then there's a couple of things that need to be considered. And one of them is grout refusal. And I put this slide right after the slide on how do you determine how much grout you want to use, because one of the differences between rock grouting and or consolidation grouting rock and permeation grouting in soil is typically in permeation grouting, you're often going to use a volumetric refusal. The reason being is because often you can push grout further than you can control the spread of that grout. And as we said earlier in some of those slides, you don't want to have an uncontrolled spread of grout. So that calculation of how much grout goes in the soil goes into your volumetric refusal. So basically, you are going to take your theoretical cylinder that you came up with, and that is going to be based off of the amount you figured you need to inject in that. That's going to be a volumetric refusal. And if you get to that point, you're going to stop grouting and move on to the next stage. You'll also have a pressure flow refusal, similar to in rock grouting. A lot of times in permeation grouting, it's going to be somewhere between 0.5 and 1 psi per foot of depth, definitely not over 1 psi, and a specified flow rate, which, you know, I have 0.2 GPM here. Realistically, you're probably 0 as your flow rate for a grouting refusal on a permeation grouting job. This next slide, I wanted to talk about permeation grouting versus compensation grouting, and I need to define compensation grouting, and I think I talk about this on the next slide. The reason that I think that it's sort of pertinent to discuss this is a lot of the times that a permeation grouting job is done wrong is because someone's actually doing a compensation grouting job. And so sometimes the easiest way to understand how to do something is to understand how not to do it, in my mind. Compensation grouting or fracture grouting, as you can see over here on the left, essentially the idea behind that is to inject grout at specific points in the soil and to actually fracture the soil. So you displace that soil. You cause a lens of grout to be injected into it. The grout does not mix with the soil, and so the lens goes in, it displaces the ground, and when it displaces it, it densifies it. Permeation grouting, the intent is to essentially not move a single soil particle. All you want the grout to do is to go into the void space of the soil and fill that space. So compensation grouting is typically utilized to either control settlement or to provide some lift of structures or whatnot, while permeation grouting is typically utilized to control water or to improve the ground characteristics, whether that's stand-up time or just ground improvement. But again, the point here is that a lot of the times, if permeation grouting is done incorrectly, it turns out to be compensation grouting, and we'll talk about why. For permeation grouting, your injection rates are typically going to be very low for what most people consider injection rates to be. A lot of the times, you're going to be at 3 gallons per minute or less, kind of at a rule of thumb. And the reason that is because, again, you don't want to move the ground. You just want to fill in the void space. And too high of an injection rate can fracture the ground and cause the lensing. Additionally, your pressures are going to be low, as we talked about, and that also is because you don't want to displace the ground. You don't want to lift it up, inject, and cause a lensing. You just want to push the grout through the matrix of the existing ground structure. So I thought I'd throw out there. Again, I thought that was an important distinction to make between different grout types and what you may do wrong. So we'll jump into two case studies quickly here. Number one is a short one. The information that's presented over here is not actually from the project. It's one of those projects that you can't talk about and you can't keep any information from. But this drawing over here is from a similar project that we're working on right now. And so I thank Clayton Blute of Gettle for allowing me to use this drawing. But essentially what that was, it was a cofferdam structure within a river where a pipe was going to penetrate through the cofferdam structure. So you can see a pipe here. There's sheets which go around this pipe, but obviously you cannot drive the sheets through the pipe. So you end up with this window around and beneath the pipe for the cutoff structure. So in this case, this was through sand. Permeation grouting was chosen to make the seal around the pipe so that the cofferdam could then be dug out and the work could be done inside of it. This one was a little bit unique in that due to the site geometry, this space was rather wide, and the soil was fairly fine with fairly high fines content, which led us to select an acrylamide simply because we had longer distances to try to push the grout, as well as we thought we may need additional time to push the grout those longer distances. So that's how that was done. This slide goes to that. The acrylamide was the lowest viscosity possible, so it could be pushed the longer distances, and it could go through the smaller particle size and higher fines content, and allowed longer pumping times. Project number two, this was along a roadway essentially near the ocean, so it was a sandy material. And the intent was that there was going to be a bypass or a off ramp essentially added to this. So if you look over here on the left in this circle, the red circle, then there was an existing road. And to make this on ramp, then they were going to have to excavate beside that existing road. So the point of the grout curtain was that it was a busy road. It couldn't be shut down. They were obviously wanted to take every precaution, didn't want any problems with the excavation of the sand beside the road, and also they wanted to improve the sand beneath the road. So there was a permeation grouting was selected, sodium silicate, a grout curtain that extended along the cut that was going to be made into the road. Here on the top plan view, at the top, then you can see that where we talked about the circles, the cylinders, the overlapping cylinders, so you can kind of see how that controls the whole layout. And then there's the depth on the profile view. So a picture, this was later in the program. Most of the grouting had been done. This was to go back and do a little extra grouting. But just to show sort of the equipment, the setup, here's a plant that's going to do a solution grout. You can see there's mixing tanks here, so there would be a side and a B side with a pump in the middle that pumped a 1-to-1 ratio out into a mixing head before it went through flow meters. This plant would be set up to inject 4 holes at a time. There's 4 hole meters or 4 flow meters here. It's important for permeation grouting typically. Since you're pumping at low injection rates, you want to be able to pump multiple holes at one time to make the grouting efficient. So that's sort of what this is showing. I said I would talk about sleeve ports a little bit more. This is just an example. A sleeve port could be, or tube of shed, could be either a PVC or a steel pipe. It has perforations at specific intervals. As you can see here, underneath these black rubber bands are perforations in the pipe. And essentially, you go down and you put a packer above and below the perforations and inflate those so you isolate the perforations. It allows you to inject in specific spots, again, so that you know you can control where your material's going. Not the greatest picture, but here there's the red circle shows a sleeve, the whole of a sleeve port that's been excavated. The white stuff around it is a encapsulation grout that's around it when it's installed. And then, as you can see at the top picture, a sleeve port is simply PVC that's it sticking up above the ground. So what does this look like when you do it? This is the site later on. I guess the important thing is you can see the grout line, the red line that was just behind the sheet piles on the left-hand side of the page. On the right would be the typical soil conditions without grouting on the site. And you can see, it's a sand and it goes in at a typical angle of repose for sand when you excavate it. But the interesting thing probably to show here is this grouted area that's back along the back picture where the guy is working, installing some lagging boards, because that's a cut through the grouted material. So this is typically what everybody wants to see. What does grouted, permeation grouted sand looks like? Here's a pretty good picture of it. This was on the left-hand side, the lagging board. That was the area the gentleman was working in. And then on the right-hand side, that sort of a blow up. And that's what permeation grouted sand looks like. Obviously, you can cut it, has a vertical stand up. But you really don't see the grout that much. You just see the difference in the characteristics. So that concludes my portion of the presentation. I'll give it back to you, Jessica.
Great. Thanks, Brad. So now we'll get into, we've got about 5 or 8 minutes for Q&A. So if you have some questions and you haven't submitted yet, go ahead and add them to the box. But I know that Britt has a few questions that have come in. So Britt, if you want to take over and go with Q's.
Yeah. Thank you, Brad. Great presentation. Several great questions in here. I don't know that we're going to be able to address all of the questions, but we'll get to what we can. One of the first questions, and Brad, I think this is going to be for you, and you may have spoken on this, but a little more clarity would be great, is what is the typical hole spacing when doing permeation grouting? And then how do you determine the different stage lengths?
Yep. Okay. So, I'm going to give a rule of thumb first, Britt. And so the rule of thumb is probably going to be that a typical hole spacing is going to be 4 to 5 feet. In most soils, let's call it 90%, then that's a reasonable distance to push a grout, and it's controllable. Obviously, there's times that may not be adhered to for specific reasons, but that's pretty typical. If you're not doing that, then you probably should have a good reason why. And then as far as a typical stage length, then a lot of times then you're looking at somewhere in the say 15 inches to 24 inch range, so about 15 to 24 foot. And again, I think that comes down partially simply to get a controllable theoretical grout zone, theoretical injection volume, but also just to ensure that you're not straddling too many different types of geologic layers.
Brad, I think people may benefit if I were to expand that question a little bit. Does your hole spacing differ based on the grout material you're using, let's say an ultrafine cement versus that of an acrylamide?
I'm going to say probably not for permeation grouting itself, Britt. I'm going to say probably not significantly, because your grout selection is really, you're going to select your grout based off of the geology, and probably not change your hole spacing tremendously. And for example, maybe an easy way to explain that is if you can inject an ultrafine cement at a 2.5 foot radius, you're going to do that, and you're not going to use an acrylamide because you don't need to use an acrylamide. However, if you can't inject an ultrafine cement, if you can only inject an ultrafine cement 6 inches, then you're going to use an acrylamide so that you can get out to the 2 to 2.5 feet. Does that answer the question, you think?
Absolutely. I think what I like about that is it reinforces that Mother Geology drives the selection of your grout.
Yeah, I would.
The goal is. So
I would agree with that.
You gave me the answer I expected, and many people on the call probably also expected that answer. So, this next one is sort of a spinoff of that question, and it's really comes into grout takes. What type of grout takes would I expect in a line of secondary holes if I've already grouted the line of primary holes? Should I expect the same or less? If that makes sense. And I don't know if we talked about primary, secondary, tertiary, or defined it, but we might define that real quick and then maybe answer the question.
Okay, so primary, secondary, tertiary. Hole orders, you're going to go, primary holes, essentially you're going to go and grout first, and they will be at a wider spacing. Secondary holes will be spaced between those, and so there will already be some grouting done. When you do, there'll be grouting the primary holes done, and so on and so forth. You can keep going on. Really, in rock grouting, that there's sort of a typical industry standard of primaries, secondaries, and hole spacings and things like that. In my experience, that is not as well defined in that order is not as well defined in soil permeation grouting. Some people that I know don't typically tend to use hole orders. They go in and do everything. Some people use what's called primary. Some people use primary and secondary holes. So you would do a set of primary holes, and then you would go in and do secondary holes that split those. However, some people use primary and secondary stages. That's a method I sort of prefer. So if your stages are typically 15 inches apart, then you would go in and do a stage at 15 inches, skip the next stage, and go up and do the next 15-inch stage. So technically you're, 30 inches apart. And then in your second round, come back and hit those stages in between. So there's different ways to do it in permeation grouting than there is in rock grouting, consolidation grouting. But I will say this, what you should expect as the decrease in grout take is going to be very dependent on how you approach that, how you design your program, if you use secondary holes or if you use secondary stages. But ultimately, you do want to get the ground to a situation to where it does not readily take grout. And that means you are going to get up to pressure that you want, and you're going to see that the flow rate indicates that it's a lot harder to put grout in the ground later in your program than earlier in your program. But it's hard to say exact numbers in permeation grouting unless you understand the program, in my experience.
Okay, great answer. Well, we've got several more questions here, but we have run out of time. So we are, any closing comments from you, Brad? You want to hand out to our attendees?
I would just say that hopefully that this has helped out, and I hope that this can be used along with the rock grouting presentation from the last time. So, if you hadn't seen that one, I would suggest watching those two, just to kind of shed some general light on the considerations for the two different types of applications.
Yeah, fantastic. I would first, my closing comments are thank you to everyone on the call, especially thank you to Brad for participating in this 2 webinar series that we've put together on rock grouting and permeation grouting. I think we've gotten a lot of great feedback on both. We did on the first one, and I've already gotten a little bit of feedback on this one in a positive light. And just a tremendous wealth of information. Grouting is always fascinating to me. The more I learn, the less I know. And but hopefully we all continue to put on our learning hats and continue to extend and expand and raise the awareness of grouting, so, and its benefits and value. So thank you everyone for your time today. Brad, thank you, and I look forward to next time, whenever the next time is.
Yep. Thanks, Britt.
All right.
Thanks, Jessica.
Bye-bye.
Thanks, everyone.